Good morning, all. We'll just start the session in a few minutes. Good morning, all. We'll just start the session in few minutes. Good morning, everyone. Just tell me whether I'm audible or not. Can you please, anybody, is my voice clear? You can type in the chat box.
Yes, your voice is audible.
Thank you, thank you, thank you.
Yes, you are audible.
Thank you, sir. Thank you. Coming to today's session, I'd like to greet you a very good morning to one and all. This is Manasa Vatsavai. This is Assistant Professor in the Department of Civil Engineering, SVCW. As you all well know that on behalf of Civil Engineering Department SVCW, we're organizing a short-term training program on soft computing techniques in civil engineering. This is phase 2 training. And you all also well known that today is the last session. This session is going to be headed by Dr. Palla Girish Kumar, Head of our Department of Civil Engineering, SVCW, Bhimvaram. Now, let me take the privilege of introducing him. Dr. Palla Girish Kumar was graduated in Civil Engineering from Sri Venkateshwara University College of Engineering, Tirupati in 2012. He has done his Masters in Transportation Engineering and Management from National Institute of Technology, Tiruchirappalli in 2014 and also he has done his PhD in civil engineering from National Institute of Technology, Tiruchirappalli in 2018. He worked as an assistant professor from 2018 to 19 at Gudalavalleru Engineering College prior to SVCW. In 2019, he joined as an associate professor at Sri Vishnu Engineering College for Women Autonomous Bhimvaram, and at a very adolescent age, he has been delegated as the head of the civil engineering department at SVCW. Coming to his work areas, he has guided one MTech dissertation and 15 UG projects in the areas of pedestrian traffic, self-healing pavements, simulation, route optimization, RAP, and also many more were on abroad. Apart from that, he has been invited as a speaker by multifarious institutions and organizations. Beside all these technical aspects, Dr. Pala has been a rock solid performer in the area of administration and external affairs too. He is the prime mover and instigator of Royal Civil Colloquium, that is RCC, established in 2019, whose cardinal motto is to expose women students to the technical and industrial aspects of working areas. Dr. Pala has also been the founder of the Career Development Program, which is CDP, in SPCW at Bhimvaram, which functions in indulging technical and non-technical skills. He also reinstated the Indian Concrete Institute chapter, that is ICI student chapter in SVCW, and he also holds a lifetime membership in professional bodies like Indian Geotechnical Society, that is IGS, and Institute of Engineers, IAME, India. In addition to all these institutional flourishments, he had organized several workshops and faculty and student as well, and has been consistently working on the various virtual programs like Stream Web Series, Digital Weighing 2K20, that is an online event platform, short-term training programs, AICT sponsored programs, and also being on the edge of organizing national virtual conference on sustainable construction techniques and advancements in civil engineering. That is SCTAC 2020. Beside all this, he was honored with National Award from the Government of Tamil Nadu for Best Project during the year 2014, Best Prapor Award for the Prapor presented in International Conference, that is FEASE 2018 at NIT Tiruchi, and he also won the International Best Researcher Award of the year 2020 in the area of Terramechanics and Nanomaterials in Pavements from IDMAS Learning Center, Malaysia, and World Research Council. And also, Dr. Pala was induced on the reviewer. Dr. Pala was induced as the reviewer of Transportation Research Board, International Journal of Engineering Sciences, Advancements, Computing and Biotechnology, and Global Journal of Research in Engineering, USA. He has blazoned 12 publications at international conferences, 3 at national conferences, and 14 plus publications in international and national journals, and a book in his account. Dr. Pala's areas of interest relates to terramechanics and nanomaterials in pavements, traffic safety, pedestrian and driver behavior analysis, self-healing pavement, evaluation and management, and traffic simulation. With this brief introduction of Dr. Pala Girish Kumar, I'd like to hand over the session to him. He is going to address on the topic of FEM applications in terramechanics. Sir, please, the stage is yours.
Yes, ma'am. Thank you so much, ma'am. Thank you,
Thank you, sir. Thank you.
Monica, madam. Yeah, such a nice introduction about me. So my
Thank you,
voice is
sir.
clear to all the participants. Is it
Yes, sir.
clear?
Yes, sir.
Yeah,
Yes, sir.
you can mute, ma'am. Yeah, thank
Okay.
you.
All right.
I'll take the session. Yes.
Okay, sir.
Yeah. So, well, yeah, I once again wish you what to say very good morning to one and all. And before starting my presentation, I would like to wish you on this occasion. I wish you happy Vinayak Chaturthi. Yes. As of now, as a part of AICTE program, we were able to see a lot of applications in water resources, a lot of applications in geotechnical, some applications related to transportation. Somehow we are able to cover something related to civil engineering and some computational techniques, some experimental analysis, something we are able to see. But today, in the final session, will something I'll take you to the space for a while. So I would like to introduce this very interesting area. Is my voice is audible to all the participants without any disturbance? So if you can confirm, I can go ahead with my session. Yes, please, someone confirm me. Yes, thank you so much, sir. Yeah, yes. So quickly we will just go through this space research, and we will see what is actually deals with and how it is and how it comes into picture, and which country is doing vast research in this area. So my topic of this presentation for this session is FEM applications in Terramechanics. Yeah, I'll try to introduce the this is your outline of presentation that you can see. I'll try to define the what this Terramechanics area is, and then I'll try to give some. Yeah, thank you so much. Yeah, I'll try to give some introduction, basic introduction in the Terramechanics area, and then later on I'll try to show the type of rovers that we are having and with landing sites, and then some research background with some FEM applications in this Terramechanics that what we have actually carried out. And later, I'll try to summarize the entire session and the presentation. And then, if possible, I'll try to show the research contribution to this research background. And then later, I'll try to show some of the references you can take. That is my publication of the work that we carried out in this research background. Then later on, I'll try to show the research scope in this area. So let me start with the definition of the Terramechanics. This Terramechanics is actually defined as the study of soil properties, especially the interaction of wheeled and tracked vehicles on various surfaces. When I say various surfaces, here two types of surfaces that we actually have. We need to consider the earth surface as terrestrial surface, the space surface or planetary surface as extraterrestrial surface. I am repeating the words terrestrial and extraterrestrial. Terrestrial is the earth surface, and extraterrestrial is something that that is a planetary surface. So normally when I take this is a Terramechanics, it all deals about the rover. Okay, rover. When I say rover, it is an autonomous vehicle, or we can simply call it as a mobile robot. So we usually see a human robot. I'm not talking about the human robot. I am talking about the mobile robot. So which means an autonomous body where it is an unmanned vehicle. So the vehicle itself moves with its sensors, its own nature. So here I'm trying to tell you the wheel or tracked mechanism. Two mechanisms are there for this rover. So for example, I will show you here what is that actually wheeled type. So this is one of the type of example I can show as a wheeled type rover. Okay, so another type is this is the tracked one. This more or less you will see various applications, like military purpose you are able to see in the terrestrial surface, as well as for the agricultural purpose also you will be seeing somewhere this kind of a mechanism. So normally this Terramechanics is defined in order to study the soil properties, especially the interaction of the wheeled type or the tracked type on such surfaces. The surfaces are extraterrestrial and terrestrial surface. This is how this Terramechanics is defined as. So now let us go to the introduction part of this Terramechanics. So here when I say the mobile robots are autonomous vehicle, or simply I will say rover. So these rovers are very important in exploring the space and plays a huge important significant role on the planetary surfaces. When I say planetary surfaces, this is nothing but the moon surface, which is a Martian surface. The Mars surface, which is a Martian surface, Martian planet, and the moon surface, which is a lunar planet. So here, these two planetary surfaces are largely covered with dust, loose soil, deformable soil, rough terrain, or some rocks, stones, ditches, obstacles, and steeper slopes, and so on, many more. So while having such challenge, this because of all this presence, the terrain is a challenging terrain. So because of these reasons, when the mobile robots are subjected to move on such a challenging terrain, there is always having a possibility to have a higher risk. The higher risk in terms of a severe slip sinkage on a deformable soil or a loose soil, that results in the reduction of tractive performance. Okay, so when it happens, obviously the mission will not move further and it gets some failure. Okay, so another reason is when the vehicle, you see the examples here, some of the examples in the slide at the bottom. So few pictures are given as a rovers that are sent to the space, and sometimes the wheels which are moving on the surface get stuck in the soil. Okay, in the soil. So because of that, it is also not able to move further. So because of this reason also, sometimes the mission gets failure, and also sometimes because of the obstacles you see in the second figure, because of the obstacles, it may divert its path, or it may be getting some problem and it may further don't move. Okay, these are such few simple problems where the mission it gets failure instead of achieving its target. I have mentioned some example here. For example, you take Luna 21, which is actually landed on the moon. and the lunar planet in the year 1973, it has traveled 37.7 kilometers, and the mission got failure because of the reason the wheels got stuck in the loose soil during its travel. But actually the rover, this Luna 21, is designed for traveling of 42 to 42.2 kilometer distance. But instead of reaching this target distance, it is able to only travel particular distance, that is 37 kilometer. After this, it is unable to move that remaining distance. So here the mission, it's incomplete. Okay, so few such reasons, few such examples also are given here. Lunar code 1, the same reason, 10.5 kilometers only it has traveled instead of traveling 20 kilometers. At the same time, MER, which is a Mars exploration rover, which is sent to Mars, and that is a Spirit. This name is Spirit, and this is under MER. So it has traveled only 7.73 kilometers. And this Sojourner, which is also Mars rover, which is traveled only 100 meters. And this is Lunar code 2, which is a lunar rover. So these are the different varieties of rovers that are sent. Apart from this, there are many more rovers are there, but in general, which have got failed. So those examples are mentioned in this slide. You can see here. And so these are the certain problems. To overcome this problem, we need to there is a necessary to study the important thing, the mobility performance of a wheeled rover which is purely based on this Terramechanics area. So okay, so I'm telling you the mobility performance we must able to read, to avoid such problems. We need to understand this mechanism. So here the mobility performance of such rovers is defined in terms of 3 performance indices, which are the trafficability, maneuverability, and terrainability. Okay, see, this trafficability is something which deals with the rover or rover wheel ability to traverse on soft wheel hard ground without any traction loss. And the next performance indices is the maneuverability, and which is nothing but the ability to navigate through the environment, which is of moist type, heavy wind type, and dusty type, which actually naturally exists on the planetary surface. And next performance indices is the terrainability, and it is nothing but the rover ability to negotiate various terrain irregularities, maybe different kind of slopes that you might having. You have adverse slope, mild slope, or steep slope, or some narrow slope, or something like that. You'll have. So because of that irregularities, it is the ability to negotiate in that kind of irregular terrains, and also during the presence of obstacles also it comes in this category, terrainability. So when you compare these 3 performance indices, so here the maneuverability, which we cannot change the environment situation and we cannot control the environment as it is, it remains as a natural one. And terrainability also, it is a natural one, we cannot re-terrain it on the space. So here 2 parameters are huge, very difficult to concentrate. And so here we have a larger scope existing on this particular performance, that is a trafficability. You can conduct the various, you can study the various parameters which comes under this trafficability, which I'm going to show in the subsequent slides. So that trafficability part is very, very important for us to understand the mobility performance, because we cannot concentrate these 2 things. So we will concentrate this particularly the trafficability. So here, so many researchers conducted research on this wheel-soil interaction, which is absolutely on the Terramechanics basis, to know the traveling performance or mobility or trafficability of wheel on soil, and also the influence of various performance on its mobility of a rover. So now let me define you something, the trafficability which I mentioned in the previous slide. It is very important, that defines the mobility performance of a rover. And this mobility performance will have a lot of parameters to study. So such parameters, the parameters also having a lot of effects on its mobility performance of a rover or a rover wheel. So what are the different parameters that affects the rover wheel or a rover? Let us see. This is a spelling mistake, so you have to excuse me. This is sinkage. Okay, sinkage is one of the parameters that also affects the traveling performance. And slip ratio is another term, another parameter that influences the mobility performance. And rubber pull is something that also influences the mobility performance, as well as the resistance. This resistance is something which is a combination of motion resistance, bulldozing resistance, compaction resistance, as well as gravitational resistance. So here another important parameter is torque. Torque is also plays a huge role in terms of mobility performance. And also some of the coefficients, like torque coefficient, pull coefficient, coefficient of resistance, rolling resistance, something like this, different coefficients are available as a parameters that also which affects the mobility performance. So here these are the certain parameters that importantly have to consider to study the effect of these things on the mobility performance, so that we can define its trafficability. Okay, so now particularly in this session I would like to concentrate more importantly on two parameters. One is the drawbar pull and vertical force. These are the two basic things which actually involves in calculating or measuring or estimating these different parameters. Okay, so now, so from this drawbar pull and vertical force, we have another important connection between the some of the functions of these two. So those functions are the normal stress and shear stress. So here the normal stress and shear stress are the functions of this drawbar pull and vertical force. Okay, this vertical force is normally denoted by Fz and drawbar pull is normally denoted by Fx. That I will show you in the subsequent slides pictures. And now, most importantly, in this session, I would like to concentrate on these functions, normal stress and shear stress, how it varies for different combination of wheels that we consider for the research study. And this normal stress and shear stress normally depends on various geometrical parameters. See, suppose I say wheel weight, wheel diameter width, and also sometimes grouges and lugs introduction. So here, see how it is relating from trafficability to various individual parameters. So we are saying mobility performance is comes with this trafficability, and mobility performance defined by various parameters effects, and various parameters are mentioned here: sinkage, slip ratio, drawbar pull resistance, torque, and various coefficients. And this, most importantly, in this session, we are concentrating on this what to say, the functions of normal stress and shear stress, which are a function of drawbar pull and vertical force. These two are also very important as a parameter to define the mobility performance. So these normal stress and shear stress are varies or depends on various geometrical parameters such as wheel weight, wheel diameter, wheel width, and these grouges or lugs. In addition to this, we have that grouger or lug that I will show you in the figure. That then that time you will able to understand. So with this, I'll try to show you what are the types of rovers and landing sites that are available. So normally I'm talking about two planetary surfaces. One is the Mars, one is the lunar. And for the Mars exploration rover, we have various types of rovers, and Spirit rover, Opportunity rover, Curiosity, and Sojourner. These are the very important space machines for under this Martian planet. Okay, apart from this, we also have Surveyor and some other important rovers as well, but I didn't mention those things here. Only I mentioned, only quoted only important machines for this MER. So another important planetary surface is lunar exploration rovers, and under this category we have Lunokhod 0, Lunokhod 1, Apollo, LRV. LRV is lunar roving vehicle. Okay, lunar roving vehicle. So in that Apollo, there are huge number of Apollo missions: Apollo 14, Apollo 16, Apollo 17, that I will be showing in the picture. Okay. So now another important thing is Lunokhod 2. These are the various types of lunar rovers that are available under this category. Okay. Now see the picture of see this picture. This is a surface where you are able to see this red color, green color. Okay, I'll try to go slow because maybe I am a little bit fast. Okay, so yeah, so you can see here red color, green color, yellow color. So this red color that indicates, that Luna. Okay, that is yeah, Luna, and this is that is Lunokhod 0, Lunokhod 1, Lunokhod 2, or Luna 21. So all those the places where that Luna 21 landed here, or Luna 0 landed here, Luna 1 landed here, like that. That is a landing site. Okay. So this green color indicates the Apollo missions, Apollo LRV. So these are the places where that Apollo missions landed, and Surveyor. These are another what to say, type of space machine that is landed in that particular place. Okay. Next picture gives you a clear explanation of this landing slides. So here various number of rovers are mentioned here, and it's a landing site. So Apollo 17 in the year December 1972, on 11th, it is landed here, somewhere here on the moon surface. Okay, and here Apollo 15, like this, you see number of Surveyor, Apollo, Surveyor, again different sequence of numbers, different rovers, and its landing sites. Okay, this is how that rovers takes place, and this is the crew that they used to go. And now one must need to understand the necessity of the study. So why we need to do a research in this area? So what actually there in this area? Okay, so let me introduce the necessity. So in the design of a rover, as I mentioned, that the rover is subjected to fail without moving the target distance. So that means that there is something need to be modified, or there is something need to be analyzed. So while designing planetary rover, it is necessary to evaluate the effect of model size parameters. When I say the model size parameters, I mean to say wheel weight, wheel diameter, wheel width, as well as the grouges or lugs. Okay, that is added to the wheel. So that definitely influence the mobility performance. So This, once you study, you are able to understand, and with by optimizing the dimensions, you are able to design the rover. Okay, so before designing a planetary rover, you must understand this analysis, this behavior. And then, as I mentioned, we have two types of mechanism. One is a wheel mechanism, one is track mechanism. Here it affects the traveling performance or mobility performance in different ways. Suppose you consider the wheeled mechanism, your wheel weight is increasing, and subjected to your rover weight is increased. Therefore, there is a huge effect on its traveling performance. Whereas from the studies that are carried out, that is inferred when you use track mechanism, when your rover tracker wheel is and wheel weight is increasing, there is no effect on its traveling performance in case of track mechanism. Okay, what I mean to say, there is no effect of weight when you use track mechanism on its traveling performance. There is a effect of weight when you use wheel mechanism. When you increase the wheel weight, it obviously affects the traveling performance when you go with the wheel mechanism. And another important inference or appraisal that we noted from the past studies are the wheel diameter rather than wheel width. It involves in improving the mobility. Okay, another important note we have made is when you add the lugs, or when you provide the lugs or a grouser, we can call either lugs or a grouser, both are same. It also affects the it also affects the traveling performance in a positive way, positive side, that improves the traveling performance. So now in this current study, I am going to show you something about the analysis of normal stress and shear stress that are generated using, I mean, that is found using different models that are available on a particular simulant which we characterized. Okay, and later on we have able to find the vertical force and rubber pull, and the vertical force is compared with the wheel weight. So okay, when your FZ is less than, far less than wheel weight, it means the wheel is subjected to a huge sinkage. So thereby there is a problem on the mobility performance of a particular rover. When your vertical force is almost near to this wheel weight, which means the effect of it, the effect of sinkage is very less. So that how it varies, we will see with the research study. So what I mean to say is we need to pay attention towards the study of various dynamic effects that are occurring at wheel terrain interface, such as the slip, sinkage, and which affects the mobility of a rover or rover wheel. We will not see about slip and sinkage in this research study. We will see absolutely about the analysis, how this normal stress and shear stress occurs beneath the wheel on the top of the soil surface, and how it varies from one model to another model. And with some comparison, we will try to finish the session. Okay, now let me show you some of the research objectives that is considered for the research background. So one is, I have mentioned here four important objectives. Out of four important objectives, I would like to discuss more importantly on first three objectives. One is the parametric study on the various suitability of various models which are available for arriving at various resultant stresses. When I say resultant stresses, I mean to say normal stress and shear stress. And also we have reinvestigated, we invented the model for shear stress distribution findings. So we call it as improved model for shear stress distribution. That also which has become an alternative approach. I will try to show that one also. And finally, the dynamic analysis of plane wheel. So this dynamic analysis we have done using FEM, which is ANSYS. So that also I will try to show how that stresses varies in the ANSYS software in the simulation part. So this is the experimental setup that we actually fabricated. This is nowhere related to our research now. So let me also show you these two pictures in the bottom. You can see these are the types of plane wheels that we considered for the study. Okay, so just give me a minute. Yeah. So this is one plane wheel. This is the wheel on the right side. You can see one kind of a setup here, one L shape. That is a provision of lugs. Okay, we call it as a grouser also. L shaped lug. So it has a certain amount of height and number of lugs we used for the plane wheel. So the different combination results we will see in the coming slides. So most importantly, in this research background, I will talk about the parametric analysis of various models on that particular simulant, and also I will try to show what is the improved model, what is the reinvented model that we were able to generate, and which has become an alternative approach with the existing scenario, with the existing model that I will discuss. And also finally, I will show some of the FEM results for this only plane wheels. I'm not talking about the lugged wheel, okay, because I didn't mention the results in this slides in the lugged wheels. Only plane wheels I have considered, so that results I will be showing in this research background. Now here you see two pictures here. This represents the wheel soil interaction diagram. This is the plane wheel. Suppose you consider, you assume this as a grouser, that it is a lugged wheel. Okay, this is a plane wheel with no grousers. This is a wheel with a lugged, with a number of lugs or a provision of lugs. So when as a wheel moves on deformable soil, there is a possibility of there is a complex interaction between takes place at the wheel soil interface. Okay, wheel soil interface, and also which is subjected to adjacent soil. So here, when this movement takes place, obviously there is a possibility to cause slip. Okay, when I say slip, there are two types of slips are available in this. Okay, when during this movement, one slip is on a flat terrain, and another one is when the rover is subjected to move on a slopy terrain. The amount of slip it is generated, it is termed as a slip angle. Okay, whereas when this moves on a flat terrain, the amount of slip that is generated, it is termed as a slip ratio. Normally on a flat terrain, it happens in the longitudinal direction, whereas in flat slopy terrain, it causes in the lateral direction. So we were able to understand this figure. From this figure, when this rover is subjected to move, there is a possibility to cause a complex nature beneath the wheel, and also there is a possibility to cause two types of slips. One slip is on a flat terrain, which is in the longitudinal direction. One slip is on the slopy terrain, which is caused in the lateral direction. So on the flat terrain, the slip that is produced is termed as a slip ratio. On the slopy terrain, the amount of slip that is generated, it is in lateral direction. It is termed as a slip angle. So now let me show you what are the various empirical relations that we actually had to investigate or to determine various types of the normal stress as well as shear stress. Here you see, suppose you take a Rees 1965, Becker 1969, Wong and Rees 1967, Yagnama 2004. These are the various people that actually given to define this normal stress for various conditions. So this theta m, theta f. So all these parameters I will try to show in the picture. So here you see different parameters. W is the wheel weight, T is the torque, and dP is the drawbar pull. And here theta m is the maximum specific angle, where you will see, you will try to see the maximum shear stress as well as maximum normal stress. So that is the basic thing that happens in this area. So another one is theta 1. This theta 1 is also sometimes can represent as theta f, and theta 2 is the exit angle. This is the entry angle, this is exit angle. Theta 2 can be represented as theta r also, because these different set of people use different what to say notations. See, someone is using theta 1 for entry angle, someone is using theta f for entry angle. So just I'm defining what is this theta 1, theta f, and theta 1, theta 2, and theta m. Theta m is the maximum specific angle, where that wheel is able to generate its maximum normal stress and maximum shear stress beneath its surface. And where theta 1 is the entry angle, it is the angle at which the wheel is making contact with the soil surface. Okay, and theta is the exit angle or the departure angle, is the angle at which the wheel departs the soil surface. So that is how it is defined. Okay, so now we will try to see different parameters apart from thetas. We have a n here. N is a sinkage constant, sinkage exponent or sinkage constant, and yeah, rho, it is the density, k phi is the friction coefficient, kc is the cohesion coefficient, c is the cohesion, and b is the wheel width, and r is the radius of the wheel. So that is all about these different parameters in these different empirical models. So now what I have done is, these different models given by different people is assumed, and I am trying to find out the entry angle and exit angle and the maximum specific angle later on through the geotechnical the geotechnical properties and mechanical properties from the laboratory investigation. We are able to find the C value and density value and Kc, Ki and N value. All those things we are able to find, and we are substituting those experimental values in these theoretical expressions, and we were able to find out the normal stress for various models. So that I am going to show you in the subsequent slides. And this is the slide that shows you the shear distribution model, which is only given by Genosi and Hanamoto in the year 1961. Whereas in the previous case for normal stress distribution, we were able to have a 4 different set of models. But whereas the shear stress, we are only having one set of model, which is given by Genosi and Hanamoto. Here you also know from the geotechnical perspective, the shear stress or shear strength is a function of normal stress, and is a function of in terms of cohesion, in terms of internal friction. So apart from that, here we are also having that another important factor j by k, 1 minus e power minus j by k. This j and k is defined in the subsequent slides. Okay, I will show you what the j is and what the k is, how these values can come. Okay, this j of theta can be found using these values. We were able to get this theta f, and we were able to have this s. S is nothing but the wheel slip, that is a ratio of wheel width to wheel radius, b by r. So from that we were able to get s value, and from the calculation part we were able to get the theta f value, and this theta will be lies between theta f and theta r. So that will be assumed with a different set of values, and with that we were able to find that this j constant. So that we are going to substitute here, and we are going to find out the theta tau of x value. So here sigma of theta, which is a normal stress, whatever you are finding for this Reese model, that sigma of theta you are going to substitute in the tau of theta value here, then you are going to get the shear stress for that particular combination. Okay, and then similarly, when you got sigma of theta for Becker model, you are going to substitute the sigma of theta here, and you are going to get the shear stress with respect to this model. So what I mean to say is, this shear stress distribution model is common in order to investigate the shear stress for different set of models that we have on normal shear distribution model. Okay, so now I will show you what are the parameters. So you see here h, sometimes we call it as wheel sinkage, sometimes we can even represent this h as a z also. Okay, some studies we will see that z is defined as a wheel sinkage, some studies we will see this h defines as a wheel sinkage, and n is a sinkage exponent. Yeah, my voice is audible to you? There is no disturbance, no? Can
Yes,
someone? Yeah,
yes, sir.
please. Thank you, madam. Yes. So n is the sinkage exponent, and b is the wheel width, c is the cohesion of stress, and r is the wheel radius, gamma, the rho is the soil bulk density, and kc k5 is the pressure sinkage modulus, and defines here. See, and here I mentioned h and kh. Okay, h defines how much the soil is compacted due to its wheel weight when it comes in contact with soil surface, and kh defines how much the soil recovers in height following the wheel when it departs the soil surface. Actually, you're supposed to question me where this kh comes in picture, where this h comes in picture, because we never seen in this model where we didn't see that kh and h values here, but in the subsequent slides, in the coming slides, you are going to see the kh parameter and h parameter when you are finding the entry angle and exit angle. Because of that, I am defining this h here and kh here. H is simply the amount of soil that is compacted due to the wheel weight, and kh is the amount of that soil, the amount of height that is recovered by the soil when the wheel is departs from the soil surface. That is very simple. If you want to find out that k particularly, you can even calculate the front wheel sinkage, rear wheel sinkage. If you do that ratio, you will get the k value. So like that, it is all the parameters are defined to use in the models. And phi, as you know that it is internal friction angle, and k is capital K. Which is defined as a shear deformation modulus, which depends normally on the shape of the wheel surface, and J is the soil deformation. Okay, that how you find out? No, you can find out using these expressions. So here you can see in the remarks without lux and with ligas what actually this represents. Here in this model also, we don't have a particularly like for with lux and without lux. We, in terms of shear stress only, we are able to have two types of expressions here. So with lux means it is a wheel with lux. Okay, without lux is simply we can call it as a plain wheel, which I have shown in the previous slide, the picture. So in this particular study, I have only considered this without lux condition. Okay, only for plain wheels, I'm able to show some of the research background that we have carried out. Okay, so with this, this is another important model for vertical force. For vertical force also, different people given different models with slight changes in different parameters. Okay, Reese is given for vertical force, Becker is given for vertical force, and Reese and Becker is commonly given as a single expression, whereas Wong and Reese is given some defined, modified version of that, and Iagnama is given a different set of expression. Okay, so here Wong and Reese is given two different conditions. One is for plain wheel, one is for lugged wheel. Okay, so similarly for drawbar pull, which is represented by Fx, it is defined here, but maybe in this presentation I didn't mention the drawbar pull because it is out of scope for me in this research background. I will try to show only the normal stress and shear stress variations, how it is causing on the TR1 lunar soil simulator. This research background, I would like to introduce. This is on the study is carried out on TRI-1 lunar soil simulant. This TRI-1 is a Tiruchirappalli one, which is India's first lunar soil simulant. This is we are able to characterize with the help of the ISRO of Bangalore, and we have a future collaborative work that we carried out, and we were able to arrive the properties of this TRI-1. And that properties are matching with the lunar soil simulant, particularly that Apollo 14 landing site properties and this TRI-1 soil properties are resembling. Okay, so that these properties are found by doing direct shear test, plate load test, and compaction test, and so on. So these are the few results that we are used in the previous set of expressions that we mentioned in the normal stress models as well as shear stress models. And now, what are the parameter details that we considered for the current study? So small wheel we considered, large wheel considered. This is small and wheel is defined based on one person given in the literature based on the B by R ratio. B by R is, that is a slip. Okay, I'll try to write. B by R. Okay, wheel width to the wheel radius. Okay, based on this ranges between 0.2 to 0.5. Okay, 0.2 to 0.5. This should be ranging between these two, and we defined the minimum and as a what to say, a small, and maximum as a large. So that we consider for the study. And 1 minute. So here two types of wheels are considered for the study. One is a small wheel and one is large wheel. So here various parameters of the wheel is given here. Suppose say you consider wheel diameter, you are able to give just a second, dear participants. 1 minute, please hold on. Very sorry for the interruption because some other people have come. Okay, sorry. Oh, yeah. So I'm defining small wheel and large wheel here. So small wheel details are given here: wheel diameter, wheel width, and wheel weight is given. And also from the experimental study, we were able to calculate the wheel sinkage. Okay, we were able to calculate wheel sinkage for this plane wheel, as well as the amount of distance traveled on that particular. Do you remember that set of bed I have showed in the previous slides? If I show you again, yeah, here. So here this is experimental test bed that we fabricated, and here this wheel is intended to move from this particular distance to this wheel. So in this we tried on doing on small wheel as well as a large wheel, so that we were able to get the traveling distance as well as velocity. So based on that we were able to find out the different required things. Okay, so that wheel sinkage is found by that and traveling distance, traveling time, thereby linear velocity. Similarly for large wheel, these are the various set of parameter details. Okay, so in simply you can see here 160 by 32 is the dimension of this small wheel, 210 by 50 mm is the dimension for the large wheel. So these are the two important wheels that we considered for the carrying out the research study in this particular area. So here now, firstly, I calculated the entry angle and the exit angle and the maximum angle for small wheel as well as for large wheel. How to find out entry angle and how to find out exit angle and how to find out maximum angle. This is very important to know us. So here, this is one of the expression given, which is based on the experimental results. H is the experimental value, that is the wheel sinkage, and R is the wheel radius. So by substituting it, you are able to get some entry angle. This theta f sometimes we can represent as a theta f, sometimes you can represent as theta 1. Okay, so theta 1, theta f both represents the entry angle. So I defined already entry angle is the angle at which wheel makes contacts with the soil surface. So that is the entry angle. So the exit angle is found by this expression 1 minus kh by r. Simply you can define that kh. The kh is the amount of soil height that recovers when the wheel departs the soil surface. Okay, that can be found by using the experiment. During the experiment process, we are able to calculate, or simply what you can do is the H is the sinkage that you can consider, K is the shear deformation modulus. This shear deformation modulus, you can even consider, calculate by doing a back stepping process. Okay, so that what we have done is, normally for low cohesion soils, this exit angle is supposed and assumed to be 0 or negligible. So we substituted this theta r as a 0, and we were able to find out the k value. Okay, and we got some value, and we substituted because we know this entry with the exit angle is not going to be larger than this entry angle. So we substituted for 14.82 as the maximum exit angle. So then we were able to find out the k value. So we understood that k ranges between 0 to 1, and we took the nearest value of this theta f, which is a 14, and we were able to find out the k value, and we got something around 0.89, and this k ranges between 0 to 1, and we substituted and assumed that k ranges between 0 to 1, and we took the average value of this as a 0.5 for the study. Okay, in order to find the theta r value. So we got theta r as 10.46. That is the exit angle. Okay, this is the angle at which the wheel is able to depart the soil surface. So that is going to we were able to find out using this expression. And now the another important this term is theta m. So theta m we were able to find using this expression a naught plus a1 into s into theta f, where a naught and a1 are the constant which is given by which is assumed by according to this Wong 1965, and these values a naught is a standard value where a1 ranges between 0 to 0.3, and so we considered a1 for three values for various combinations, because we don't know whether we need to consider 0 or we don't know we need to consider 0, because we want to study the amount of difference that comes with the various set of values. So we studied a1 taking a 0 minimum value and the maximum value as well as the average value, okay, between these two. So we considered the three values for a1, and we know this s is the b by r. Suppose you use a small wheel, b by r is different. B by r is a 0.4 for small wheel, and suppose you use for large wheel. For large wheel, b by r is 0.48. So by substituting simply, you know that small wheel, you know the exit angle. So you know the entry angle. Sorry, the theta f is the entry angle. So you know the entry angle, you know the slip, and you know different values of a1. We have three different values: minimum, maximum, and average. So now you are able to get three maximum specific angles. Okay, three combinations, three cases: theta m1, theta m2, theta m3. That I am going to show you here. Next, coming subsequent slides. So in the previous slide, we were able to do for small wheel. Here, this is for large wheel. The similar trend, similar passion we followed. We were able to know the sinkage of a large wheel. We are able to substitute. We are able to get the theta of entry angle. And we know k is ranging between 0 to 1. And we assumed k as 0.5, the middle value. And we were able to get the theta r value, that is exit angle. And by substituting this theta f and that the wheel slip in this equation for a different set of a1 values, we were able to get three different values for maximum specific angle. What do you define? How do you define this theta m? That is a maximum specific angle. This maximum specific angle is the angle at which you are going to get the maximum shear stress and the maximum normal stress beneath the wheel. Okay, that is important. You have to remember. Now this table represents the entire set of results for entry angle, departure angle, and maximum specific angle. So I considered I gave here two categories. One is Reeves, Becker, and Wong-Rees. So these three models I gave as a first category. Second category, Yagnamma model, because according to this person, this Yagnamma, this the maximum specific angle is something different. The way of approach of finding the entry angle and exit angle in this model is similar to that of previous models, but whereas finding the maximum specific angle for Yagnamma model is different. The way of approach is different for finding the maximum specific angle. Okay, that is why I gave in different section. So here in Yagnamma defined, you can able to find the maximum specific angle by assuming exit angle as 0, that is first case, and exit angle as this exit angle. Okay, suppose I consider this is theta 2. So theta 2 initially you have to consider 0. Okay, assume as 0, then you are going to substitute theta 1 plus theta 2 or theta r plus theta f by 2. That gives you this maximum specific angle, but that is first case in this Yagnamma model. And second case is you consider that theta equal to theta 2 equal to theta 2. Okay, so when you consider this theta 2 as 10.46, and you know 14.82 plus 10.46 divided by 2, that is summation of the mean of these two gives you 12.64. That is how this maximum specific angle is defined in case of Yagnamma. Okay, so like that we were able to find three set of values, whereas other models this theta m varies for this a1. So because you know this a1 considered three values, we were able to find out theta m, three theta m's. Okay, So whereas for Vietnam model, this theta m is different. Okay, this theta m is not defined by this expression. The theta m is given as the summation of this or the mean of this entry angle and exit angle is defined as mean specific angle in case of Vietnam. Okay, so in that case, theta r or theta r is considered as 0 in the initial case, and theta r is considered as theta r in the second case. So like that, we were able to find the maximum specific angle. Now our job is, our interest is to find out the stresses. Okay, shear stress, normal stress, and shear stress at 4.9 5.93 degree, and similarly 6.82 at 7.71. So for various specific angles, what are the shear stress and what are the maximum stress? Okay, this theta m you are going to substitute in the previous models, which I have already showed in the previous slides. Now I will show you what the theoretical investigations that are carried out on finding the shear stress beneath various rigid wheels. When I say various rigid wheels, I consider two plane wheels. One is a small wheel and one is a large wheel. For this and the comparison also I can show you. So now let us see some figures here. So this is the first model. You have seen the expression for the first model. You have here different set of legends here. You see rho 1, this is the minimum density, and ns is the normal stress. Rho 2 is the maximum density, ns is the normal stress. SS is the shear stress, and K1 is the shear deformation modulus at K1. Maybe you might be having doubt, what is this K1, what is this K2, what is this K3? Let me show you that K1, K2, K3 in the previous slide. Yes, here. That K is nothing but shear deformation modulus. This we obtained using the plate load test. So this as comes as 1.022 plus or minus 0.76 centimeter. So we don't know now what value we need to consider for this study, because we need to analyze how it varies. Is it varying largely or it is varying very lessly? Something like that we want to investigate. So what we did is minimum value we have taken, maximum value we have taken. At the same time, we took the average. So like that, it has come three values: K1, K2, K3. 0.0026 meter, 0.0103 meter, 0.018 meter. Okay, K1 is the minimum value, K3 is the maximum value. So you can simply remember that K1, K2, K3 for this shear deformation modulus. So for this particular K1, you are going to find out shear stress. For particular K2, you are going to find out shear stress. For particular K3, you are going to find out shear stress. Okay. So now I will go to the results now. So now you are able to see something here in the graph, in the legend. So SS rho to K1, which means for a maximum density, the shear stress at K1. Okay. For a maximum density, shear stress at K2. For a maximum density, shear stress at K3. Okay, I hope you are understanding. And here simply SSK1 represents the shear stress for a minimum density at K1, shear stress for a minimum density at K3, shear stress at a minimum density K2. What is this minimum density and maximum density? So from the results, we were able to show you something here: density, sigma, rho minimum and rho maximum, 1.15 gram per cc, 1.88 gram per cc. For these two combinations, we were able to determine the stresses. So that is how this shown here. So now you understood the legend that is given here. Now we can see the similar legends are given for the subsequent slides also for different models. No, now we should understand, we should infer something here. So we got some inference in this slide, in this figure, as the normal stress. If you see the first line, this is the normal stress line. Okay, the x-axis is a maximum angle, maximum specific angle in degrees. The y-axis is a stress. It is a normal stress as well as shear stress. Yes. Now this is the first line indicates the maximum. This is the maximum of the entire normal stress combinations. Okay, and this violet color or something, this color indicates the maximum shear stress for this angle. Okay, so these first two lines indicate the maximum normal stress, maximum shear stress. Now the inference that we made is normal stress decreases with increasing this theta m value. Okay, when you see this is the first theta m, you will get this one, and second theta m, what is your normal stress? You are going to reduce. You are going to get the less value compared to the first one. So the normal stress decreases with increase in theta m value. That is first inference that we were able to make. And next one is the minimum. This is rho 1 is the minimum density. Minimum density induces minimum normal stress. That is this line, third line. Okay, minimum normal stress is induced by minimum density, whereas the maximum normal stress is induced by maximum density. That is the second one legend you can able to notice here. So that is another inference that we made, and this trend is similar to all models. Okay, maybe it is differs with the values. Okay, we were getting different set of values, but the trend is same for all models. Okay, and another important inference that we made is the maximum shear stress. You see the second line. You see the second line. The second line from the legend 1, 2, 3, 4, 5, fifth one. So SS rho to K1. So we were able to notice the maximum shear stress arrived for a maximum density at K equal to K1. Okay, for a minimum value of K, we were able to get maximum shear stress in case of maximum density. Okay, so that is the inference that we were made, and in common we were able to say shear stress decreases with increasing K1 value. Suppose you take this is a K1, what I am saying, for maximum density K1 is this value. For a maximum density K2 line is this line. From bottom it is fourth line. Okay, so we were able to understand and get the inference from these results. The shear stress is reducing with respect to shear deformation modulus. Okay, when you keep on increasing K1, K equal to K1, K equal to K2, K equal to K3, you are able to get the maximum shear stress when K equal to minimum, that is K equal to K1. Okay, that is the one of the most important inference that we drawn. And next important conclusion from this figure we can draw is the maximum normal stress. You can take this normal stress, this is maximum normal stress, this is maximum shear stress. We were able to obtain when theta maximum is a minimum. Okay, this is the minimum, right, compared to all theta m values. Suppose this we consider as theta m1, theta m2, theta m3. So compared to all theta m's, this is the minimum specific angle where you are going to get the maximum stresses value. Okay, rather than increasing in what to say theta m values. Okay, for and that too for maximum density we are noticing. Okay, so we are noticing the maximum values for maximum density at the minimum maximum specific angle theta m1 when theta m equal to when theta m1 we are able to notice the maximum specific, maximum normal stress and maximum shear stress. This is the inference that we should draw, and we have drawn from this figure. So similarly, for the large wheel also, the similar set of inference, you can same phenomena happens here also. I don't want to explain much about this because you see, similarly, normal stress is maximum for a maximum density, that rho to ns, that is first line, and second line is shear stress becomes maximum when K1 equal to K equal to K1 for maximum density, where the rest all falls under below this category. So similar. So I will show you something linear regression equations that are drawn from the previous results. These are the linear regression that we get, that we are arrived for different set of cases. You see normal stress when density is maximum, and normal stress when density is minimum, shear stress when density is maximum at K equal to K1, and for minimum density at K equal to K1, and maximum density at K equal to K2, something like that. We were able to draw linear regression expressions for this different models. We were able to see the R square value. Okay, we were able to get some R square value near to 1 in everywhere, near to 1 and exactly 1 value. So we were able to get the fit value here. Whatever the results we found, the natural normal stress and shear stress, we were able to get the fit value. So you can see this is similar to all other models. So whatever inference I kept here, I already mentioned in the previous slides. We were able to notice normal stress decreased with rise in maximum specific angle. Yes, the minimum density induced in minimum normal stress, whereas maximum density induced in maximum normal stress. Yes, and this inference already I have told. Okay, shear stress is a maximum, at K equal to K1, and maximum normal stress and shear stress appeared at the maximum specific angle when theta m equal to theta m1 for a maximum density rather than increasing theta m value. So that we were able to draw. So similarly for Becker model also, I have given the small wheel results as well as for large wheel results. So I'm not going to explain much about here because the similar fashion and similar phenomena happened in this model as well. But only thing is you can notice the different values that arrived. Okay, in case of Rees, what is the value of normal stress, the maximum value, what is the minimum value, what is the maximum value of shear stress at different conditions. So those values varies, but the phenomena is same, the trend is same for all the models. And this is the linear regression model for Wong-Rees model. And now different inferences are drawn. For example, you see here the normal stress is up. These are the important inference from all the results from theoretical investigation. The normal stress obtained is a maximum for Wong-Rees model. As we all know now from the research background, I consider 4 models for determining the normal stress. One is the Becker model, Rees model, Wong-Rees model, Yagnama model. Okay, these are the 4 models. Out of 4 models, when you compare the results, we were able to arrive the maximum normal stress and shear stress values. Suppose I'll take individually, like I will take first consider the small wheel, and later I'll consider for large wheel. Okay, when I consider small wheel and compare the normal stress, shear stress for different set of models, I noticed we got inference that Wong Rees model is having a maximum normal stress shear stress compared to all other models for the small wheel type. Whereas when you compare with the large wheel, okay, you take large wheel and compare with all other models, you are able to get maximum values for Rees model. In the last point you can see. Now you compare with the small wheel and large wheel results, comparing with all models, your large wheel is having a great normal stress and great shear stress for the model Rees model. So that is the 3 important inferences we were able to draw. Okay, so that is important. Now, yeah, fourth model. So everything is fine now as far as the Wong Rees Becker, because theta m is same for all those values. But for Yagnama model, the measurement of theta m is differ from the other models. So we should also understand the what is the phenomena that happens here. Okay, here we have two theta m's here. When your entry exit angle is 0, your theta m is 7 point something. When your theta r, when your entry angle is when your theta 2 is theta 2, when theta 2 equal to theta 2, when you consider, this is the theta m value. So how this has comes into picture. So different set of results we are given here. So from this we were able to draw, when you consider only this fourth model, okay, when you consider only for this fourth model, you are able to get the maximum values, normal stress or shear stress for small v. Okay, whereas the earlier cases for 3 existing models, we were able to notice the maximum normal stress shear stress in case of Rees model for a large wheel. Okay, but here it is vice versa when you use fourth model. Okay, so now we have defined, okay, we were able to understand we have only one shear stress distribution model, which is given by Genosi Hanamoto 1961. So whatever the normal shear stress models you have used, finding out the Becker or Wong Rees or Wong, so all these models, the same sigma of theta values are used in the tau of theta, and you are able to find the shear stress. Now we understood that there is whatever form expression that we had in the previous case, there is no involvement of geometric parameters. So we want to see the introduction of geometric parameters, because when I talk mobility performance, at most important things are wheel geometric parameters. So that is the important parameters that plays a huge role in defining mobility performance. So we want to just test, we want to analyze when we introduce geometric parameters into the expression, how it varies. So that was the basic idea we got, and thereby we have used the results whatever we got previously. Using these results, based on the existing results, we were able to arrive this new shear stress model, which is introduced with our study. So we gave here tau equal to W by BD into A into theta m by theta reference plus B. So theta m, all as usual, maximum specific angle, this is the reference angle. A and B are the shear deformation constants, and W by B dV, these are the geometric parameters that we introduced. Okay, this is how we wanted to reinvent this tau value. Okay, but later in the initial stage, this is the expression we arrived, but later we have generalized this expression to one single expression. Suppose I'll try to disclose. Suppose see this slide. This is a modified shear distribution model. Research is carried out on deriving modified analytical expressions for finding a shear stress distribution, which we named it as modified shear stress model (SSM), which we usually use it to find the shear stress that happens and that occurs beneath the plane wheel. And we considered for the study the simulant, that is TRM and lunar soil simulant. We considered for the present study. And we know that 4 models which are existing: Rees, Becker, Wong Rees, and Yagnama for normal stress. These normal stress values are used in the shear stress model, which is already determined by Janos and Hamamoto, and we were able to get shear stresses. So we understand that there is an amplitude exists for modifying the model by introducing the various parameters. So such way we were able to introduce the modified model in order to determine shear stress beneath the wheel. So now, after achieving, after So let me introduce this. So for first model, the Reese model, when you consider the first Reese model, for that we were able to define this tau. Okay, so for different set of models, so suppose as Reese model, Becker model, Wong Reese model. So for Reese model, we were able to arrive this expression. We were able to give the relation here, but here A and B are two constants are defined in terms of k value. Okay, so here F also you can see another important shear deformation constant F, and F varies with here for different densities with respect to densities. For a maximum density, you are going to use this expression. For a minimum density, you are going to use this expression with irrespective of the geometry. This obviously when you use small wheel, this B changes. When you use large wheel, this B changes. That is not worry for us. Okay, when you use a minimum density, you can go with this set value. When you use maximum value, you can go with this set value, and thereby you can substitute here. Also k is also a different shear deformation modulus, that is k ranges between so and so k1 k2 k3. So you can get the a1 a2 a1 a2 a3 b1 b2 b3, then thereby you get so many values, shear stress value sets. So like that, we have defined this model for Reese model, Becker model, Wong Reese model. Okay, so now I'll show this is the figure that represents how to find out F value, which depends on B by W, W by BD, and B by R. So this and all not that much necessary to explain you much. So I'll just show you how we have derived. So everywhere you see the common expression, but this A and B constants are changing with respect to model. So earlier you have a and B in terms of k. Yes, of course, here also A is in terms of k, but this A and B constants changes with respect to model. When you use Wong model to define normal shear stress, you can use this shear stress model with respect to this A B values in order to define shear stress distribution. When you use normal stress, when you use Becker model to define normal stress, you can use this shear stress model with respect to this A and B. So you are getting lot of set of different set of shear stresses. Similarly, for Wong and Reese, you are able to use this model with respect to this A and B. So here, so these are the different pictures that we are able to find A and B, the constants in terms of k value. Yes. So when it comes to the discussion, what actually I want to tell from this modified shear stress distribution model. At first, I would like to tell you that, yeah, shear distribution constants A, B, and F are introduced as a function of shear stress. That is the first thing I wanted to tell you. Okay, but earlier these are not there. These are not mentioned as a function of that shear stress. So we were able to introduce these parameters, which are very crucial in terms of finding the mobility performance. Now, the second one is, yeah, it was found arrived modified shear stress models. So what we have done is using this model, whatever I am saying, this model, this modified model, we were able to reinvestigate the shear stress values. So what we found is the values we get using this new model, it is almost matching the Jonosy-Hanamoto model, which is almost matching the Jonosy-Hanamoto model, which is the existing model. So what we understand is we can use, also we can see the effect of geometrical parameters, effect of various constants on the shear stress. Okay, and this hence therefore we concluded this model, this is the model which can be used for any kind of simulant. Obviously, when you change the simulant, suppose I used for this study what to say, TRI1. So Tiruchirappalli 1 lunar soil simulant is considered for this study. So for this study, the K values varies. So we conducted direct shear test, plate load test, and compaction test. We are able to get the values. So K ranges between K1, K2, K3 that we already seen in the previous slides. If you use some other simulant, suppose say Japanese simulant, because this research is happening in various countries like Japan, Russia, and China, and US. So there they are having a lot of richer scope in this area. So they were able to have a lot of kind of different simulants. Okay, so those simulants also you can consider, and you can use those simulant values, the geotechnical and mechanical properties of that simulant, and substitute in this model. You are going to get the values, which will give you the most accurate result as compared to the previous existing one. The added value is in this here is you are going to introduce these geometrical parameters and constants, the k simulant values. So that is very important for us. So here I mentioned what is A, what is B, and I mentioned what is F here, and you can see here this is the generalized expression that we were able to arrive for modified shear stress model that is given by our research work. So now this is the final results that I can represent in the tabular column. So you see this is a small wheel for maximum normal for the normal stress and shear stress. You are able to comparing these two, the normal stress and shear stress, the maximum normal stress arrived for Wongeries. Okay, this is the Wongeries. So here, same shear stress is maximum arrived for Wongeries, 26.34 Newton per mm square. So shear stress normally. So minimum shear stress and maximum shear stress. Whereas in large wheel, if you take, you are going to get the maximum for Rees. Okay. So in comparison with the three models, don't bring this Iagnamma into picture now. Okay, first let us compare the only three models: Rees, Becker, and Wong for a small wheel. Okay, among normal stress and shear stress, you are able to get Wong Rees as the maximum. Here also Wong Rees as the maximum for shear stress. Whereas for large wheel, you are going to get the maximum for Rees model, and here also Rees model. When you compare Iagnamma for large wheel with small wheel, you are going to get a maximum values for Iagnamma model for a small wheel 27.36, whereas here you can get only 22.94. Whereas for the rest of the cases, you are going to get comparing entire wheel combination, entire models, you are going to get for large wheel, Rees model is the maximum shear stress that is going to arrive and maximum normal stress that is going to give. So this is the inference that is drawn from the study. And another important terms that I introduced from our research is two important stress ratios I have introduced. One is dimensionless normal stress ratio, and one is dimensionless shear stress ratio. Based on the results that is obtained here with various combinations, I am able to establish some relation as a sigma. This dimensionless normal stress ratio is given as sigma max divided by sigma max of at most value. Okay, so this is the relation we are able to give, and we were able to draw for different models, three models. Okay, Rees model, Becker model, Wong Rees. So from this uh, dimensionless ratios also, you are able to find the maximum DNSR value or DSSR values for Wong Rees for small wheel, whereas in simply for large wheel, you are able to get for a Rees model the maximum values. Comparing these two, you are able to get 1.7 and 1.6 as the dimensionless constants for Rees model, which is a maximum value compared to the small wheel. I think with this single figure, you are able to understand the relation. So what I mean to say is, for small wheels, when you compare these three models among each other, Wong Rees is giving the maximum. When you consider the large wheel, when comparing these three models, you are going to get the maximum for Rees model. Okay, when compare them small and large, you are going to get the maximum values for Rees model alone. So this is the kind of relation and new concept that we introduced. Even with this DNSR and DSSR also, you are going to define your maximum shear stress, maximum normal stress. Now, yeah, using that previously established results as well as the experimental results of the simulant, we were able to incorporate all those things in the vertical force model, which actually I have showed in the previous slides. We were able to arrive, vertical forces for that particular plane wheel. Okay, plane wheel. So different wheel weights. This actually, I'll skip this part, okay, because this I'm not going to concentrate more. So now, as of now, we were able to see some kind of experimental results for the simulant, and then we were able to see some theoretical investigation, how we consider the experimental results, and how we consider the empirical relations, and how we have defined the theoretical analysis. So that and all we have seen. Now let us see some of the modeling part and simulation part on which to define these stresses, okay, to see the variation in stresses. So for this, I have used SolidWorks to model our test bed as well as the wheel. So, and this is, you can see this is a set of lug. Okay, so this is how, this is the plane wheel, the test bed, and this is a wheel that with the addition of lugs. So this L-shaped lug we have introduced. This lug height is normally ranges between 5 mm, 10 mm, 15 mm. We considered for the study, and number of lugs are 8, 12, and 16. But now I am not going to discuss about various different heights of lug as well as different number of lugs. I will just concentrate on plane wheel alone. Okay. So, but this is the normally work that we've done using the SolidWorks software in the modeling part. What we have done is we have initially created single element. I mean single parts, individual parts. The test bed as one part and wheel as another part. We were able to mate it. We will. This is the model that you can see after making the test bed with the plane wheel. And then this is the previous one is a small wheel, this is for large wheel, this is a large wheel which is a 210 by 50, and then this is the test bed. You can see with the model after mating of the large wheel on the test bed. Now what are the, now this we have to incorporate, we have to import to our ANSYS or Abacus in order to simulate this uh, wheel. And now, what are the input parameters that we used in the simulation using ANSYS? So we gave the cast iron properties and as well as the steel also, because our material, our wheel is manufactured and prepared with the cast iron. So I gave here cast iron as different properties, whatever the default values, I'm able to give the default values. And these are the soil properties which we got from the experimental results. We were able to give input, and then we were able to get the results like this. So we used ANSYS, we gave certain boundary conditions, like we gave initial coordinators, and then we were able to give some force velocity which we were able to find from the experimental value, and we were able to give a joint rotational velocity. These are the certain boundary conditions we were able to give. You see the first one is the plain one and with the mesh one, and the third one is shear stress, as well as the fourth one is a normal stress, something like that you can see. So different conditions are given, and we were able to make it move a particular distance, and we were able to get the maximum stress and minimum stress, and maximum to minimum with certain different values. So this is for dynamic analysis for small wheel, and this is for a dynamic analysis for large wheel. For large wheel also we were able to give some transient. We used transient interface for this. What to say, dynamic analysis using ANSYS. So in that interface, we were able to give certain boundary conditions, the force, velocity, joint rotational velocity, fixed supports, all those conditions we are able to give, and we were able to analyze the normal stress, shear stress, as well as equivalent stress, as well as deformation as well. Okay, so finally we were able to draw some conclusion here, the dynamic analysis part, stress results in FEM. So these are the for the small wheel category and the maximum large wheel category. So what is the load applied for this? The wheel weight itself we applied as a load in the ANSYS part. So 52.18 newtons is 67.44 newtons. So with this we were able to get some stresses values, and these values we just we don't want to compare with the theoretical, because obviously the theoretical values and numerical values varies largely, or with less comparison, but we just want to see how it varies. But importantly, we were able to get some closure relation between the numerical as well as the theoretical analysis. Okay, so now that is all about the FEM analysis for this particular cases for small wheel as well as for large wheel. So now I want to show you, as I told you, like we introduced, we reinvented, we modified the shear stress distribution model. We name it as modified shear stress distribution model, that is SSM, and that values are predicted as like this. These actual values are the setup values that we already seen, 23, 23, 26, and here when you use the new model, we were able to get the values. So when you compare these two, we were able to at most very close error. The error is less than 5%. Okay, which is very closely we were able to get the values. Okay, so this is why we told whatever we modified, we invented, or we given the modified model, that model can be used for other simulants as well, because it is giving, and it can be used as an alternative approach, since it is giving the closest values with the existing shear stress distribution model. This is for shear stress. This is for large wheel. Okay, so now I will talk about the summary. So now, I have showed you the various analytical work that we carried out, the theoretical investigations that are carried out on small wheel, large wheel, in order to define the normal stress and shear stress based on the various four models that Wong-Rees, Rees, Becker, and Yagnamma. Whereas we found that shear stress is only defined by one person, and we want to remodify by adding geometrical parameters and some deformation constants into picture. So then we were able to establish a new model, and new model is giving the similar results as that of the existing model. Hence we concluded this model can be used as an alternative approach for determining shear stress by considering the shear deformation constant, as well as the geometrical parameters, when you want to see the exact effect of these parameters on the mobility performance. Okay, and we were able to see the normal maximum stresses occurs for this model comparatively with a small wheel in case of large wheel. When you take AICTE into account, you are able to see the results, vice versa. Okay. So now with this, I would like to also add something like, as of now, I have showed only the plane wheel. Maybe you can consider this study in order to for introducing the lux also, as I showed in the modeling part. Okay, so yes. So finally, the modified shear stress model, that is SSM, were derived for 3 models, and it has become a unified model. So the study can be extended for other simulants also. I have only considered TRI1, which is our simulant. Okay, you can consider the Japanese research simulant. You can consider somewhere we have a lot of different 32 simulants are there. Okay, 32 simulants are there. You can study 32 simulants for this particular combinations. Okay, so finally, this SSM satisfies the Genoese model, which is considered for the study, that gives as an alternative approach for analysis based on the geometrical parameters of the wheel, because the error found between the actual and predicted results are less than 5%. Okay, so this is the final conclusion. You can do this with other simulants. So with this, I would like to just show my research contribution, what actually we have done. This is already discussed in the previous slides. Yes, we were able to view this model. Okay, we were able to view this model in terms of geometrical parameters and in terms of these constants. Yes, and this is found to be less than 5% when compared to the actual model, and hence we can consider this model for doing the analysis with various simulants also. So that is the two important contributions with this. And also an attempt has been made on doing numerical analysis and found the results are close to the theoretical analysis. That is also one of the important contributions we made through this research. And now I'll just quickly show uh, the references and publications. Sorry, I need to erase this. Just give me a second. Yeah. Yeah. So now these are the references that you can consider in the publications that we had carried out. I mean that we published based on the previous work I have mentioned or explained in the previous slides. So 3 important publications. So I have one more publication with the same work that I did mention, as it is not that impacted journal. So only these 3 important journals are there. So you can see. Okay, so 2 more journals are there. We have published on the same similar work that I didn't mention. Only 3 references are given. And now let me also tell you, because I have time 10 more minutes, so just 5 more minutes. I'll just tell you what are the research scope that we can have. As I mentioned, mobility is a very important parameter that we supposed to concentrate. The trafficability. Okay, so here see how this the picture represents. See, this is the wheel, that is the rover that is getting stuck in the soil. Okay, simulant, that is a soil on space. So this is the problem. This is the mobility problem, that this rover is having poor mobility. It is further can't be moved. Okay, so there you can focus. Okay, this is how wheel is stuck in soil. This is the problem. This is can be focused more. And another important future scope, on the rough terrain. So during the rough terrain also, you can see the mobility, how it can have the mobility performance on the rough terrain. And next one is, sensitivity ability, sensing ability. So you see the rover is moving, but in front of you are able to have some obstacles. Sometimes it will stop, okay, but it is not supposed to stop. It has to detect and identify. Maybe it can even divert its path and can go somewhere else. Okay, so it can find another path so that it can explore the remaining space. So it is not like it is not supposed to stop with this obstacle. So sensing ability can be concentrated. That also indirectly or directly improves the mobility performance. Another important one is this one, climbing ability. Okay, when a rover is moving, when you have obstacles, sometimes here sensing ability, if you improve, it will divert. Okay, it will divert its path. So when you divert its path, it will continue to travel. So thereby your mobility is good. So this is another chance of scope. Climbing ability, you can improve the climbing ability. Okay, so thereby you can have a good performance, good mobility. And another one, you see, this is also climbing ability. Okay, this is also climbing ability. Like this, these are the different research scopes. You can concentrate on mobility of rough terrain, and when the wheel stuck on the loose soil, how to address it, and how to address the sensing ability, how to improve the climbing ability. And another thing is, yeah, this is the sinkage. When this is the amount of sinkage rut depth it causes, because of this, sometimes it is very hard to drive it further, and there's a sinkage effect. If you have a huge sinkage, it is quite difficult to travel. I mean, this is the problem where a few machines got it is not able to travel the desired distance. So you can concentrate on sinkage effect also. And another important scope is suspension type. We have a certain suspensions that is useful for climbing different slopes or moving forward. So you can concentrate on suspension type also. This also indirectly or directly improves the mobility of a rover. So these are the different examples I gave: A, B, C, D, E. So how it is climbing and how these suspensions are working. So a lot of internal mechanisms are involved in this in order to understand. So suspension moments are very important for us. These are the different set of examples for in terms of Curiosity rover. These are the Curiosity rover suspension types that they are actually used. So suspension or climbing ability. So if you use a particular proper suspension type, the climbing ability is directly gets a good climbing ability. So this is simply the plain terrain or slopey terrain. You can see how it is, that suspension is helping to climb and move. Okay, this we call it as a roper bogie suspension. So we have a different set of suspensions, or you can even design your own suspension type as well. With this, I would like to conclude. I would like to thank the every participants for thorough patience for hearing this new research. I don't know how far it is okay with you. Now you are allowed to have some questions. Thank you. I think now 12:30, 12:25. Yes. Thank you so much.
Thank you, sir. Thank you for the excellent session. Uh, Thank you for the nice and clean presentation. Now I request the participants, if you have any questions, you can directly type them on the chat box, or you can unmute yourself and you can directly access Dr. Girish Kumar.
So we'll have 5 minutes questions, then we'll take feedback. Then we will close the session, entire program. Thank you. Thank you so much to all. Thank you. Yes, definitely I will share the PPT, sir. Thank you. Thank you, sir. Thank you, sir. Thank you. See, it is a it is a multidisciplinary and interdisciplinary where you can use the civil applications also. Maybe if you are working, if you want to differently work from others, maybe you can opt this kind of different concepts. Yeah. Yeah, it is a new concept. Thank you. So I think maybe I'll consider this. We'll stop this for here. Maybe I don't have any other questions. Okay. Yes, definitely. Now we will take feedback. Maybe Mansa, madam. Hello.
Sir.
Yeah, I think they are not asking any questions. That's okay.
Okay.
People can give a feedback. I mean,
Dear
they can orally.
participants, you can we'll provide the link. You just you can give your feedback there.
Yeah.
Yeah, we'll
Using
provide the link.
feedback. Yeah, feedback. Is it possible to simulate in MATLAB? Yeah. Yeah, MATLAB also can be used. Otherwise, we can also have a console. Also, we have another console software. If you have heard about console, that console also can be used for such kind of analysis. Even MATLAB also nicely helps in doing this, particularly path traveling or path planning thing for rovers. Maybe that MATLAB is a huge importance. Huge, it will play a very nice role. But ANSYS and Abacus, ANSYS gives you more results, accurate results than Abacus for this kind of work, because I considered in Abacus first, then I found some problems, technical problems, then we shifted to ANSYS, then we got some similar results. Okay. Yeah. So definitely. So with this, I will stop this. Just I want to know your valuable feedback through oral. You can share your feedback. Anyhow, we will present the feedback link with you maybe after 5 minutes, and also we will share the assessment link as well. Now you are free to talk about the sessions, all the sessions.
Sir, good morning, sir.
Very good morning, sir.
Sir, I am Dr. Kiran Kumar, sir.
Sir, sir.
Yes, sir.
Yes,
Sir, actually,
welcome, sir.
we
Thank
are
you, sir.
unfortunately we are not following from the beginning itself, sir. Actually, 12th onwards, online classes also started, sir, in our college. So,
Okay,
but
okay.
anyhow, meanwhile, afternoon or morning, we are attending this workshop, sir. I am very thankful.
Thank you,
Uh,
sir.
Actually, this topic is somewhat is a new topic now, sir. It's Terramechanics.
Yes,
So on that, the
Terramechanics is a
last
new
two,
area.
sir,
In India, very less people are doing, sir. IIT Kharagpur and IIT Madras and NIT Trichy. Only these three places we are doing.
sir,
Uh,
are you apply a patent, sir, for this?
Patent we actually got for Muthukumaran, sir. You heard no last session. Actually, sir got
Yes,
patent
yes,
for this TRI1 simulant. For this model and
sir,
all, we were just applied. But for
sir.
simulant, we already got a patent for this.
Oh, so suppose if this Corona period will stop, we will visit your college by organizing one event, sir.
Definitely, sir.
I, uh-huh.
Definitely,
Okay,
I
sir.
will come, sir.
Thank you.
Yeah, thank you, sir.
Actually,
Thank you for your presence.
I informed to my HOD also.
Okay.
He also conveys wishes to you, sir.
Thank
Dr.
you, sir. Thank you so
Srinivas
much.
Reddy.
Yeah,
Okay,
sure,
sir.
sure.
Thank you, sir.
Thank you.
Thank
Thank
you.
you for your presence, though you are having online classes. Thank you. Yeah.
Thank you, sir.
Hello.
Hello. Yes, sir.
Sir, I am Dr. Nageshwara from VNR VJIT.
Sir, good morning, sir. Good afternoon,
Morning,
sir.
sir. Good afternoon, sir. Very good session, sir. Really wonderful and the soft techniques for geotechnical engineering and other civil engineering projects. Very wonderful to listen you, and they have taken a lot of pains to arrange very excellent speakers.
Yes,
And
sir.
also another additional advantage from you is you have put every session in YouTube. That enables everybody who is not able to present because of the online classwork and other activities. That's a wonderful facility you have created, sir. Very good, sir. Keep it up, sir.
Yes, sir.
And
Thank you,
such
sir.
type of webinars we are expecting still in future. Thank you.
Yes, sir. Definitely, sir. Thank you for your presence, sir, throughout your presentations. Thank you,
Thank
sir.
you, sir.
Thank you for your work. Yes, sir. Anyone else? I will just share the feedback link also. Anyone else would like to add something, you can add. I have posted the feedback link, you can give. So meanwhile, someone can talk if you have anything to tell you. Someone asked about more Coulomb cases and all, whether we'll consider it for this study or not. Actually, we never looked into more circle because it's purely a weak soil interaction. It's not related to only soil. So our interest is to define mobility. That mobility is nowhere related to that more for more loss or whatever it is. Yeah, yeah. Maybe in future, maybe I will consider to see, because we have a very less cohesion, some cohesion problems also there, because with the soil we are now, it is nothing to do there, because we are not going to stabilize, or we are not going to see modify the soil there. We are only subjected to the simulant or terrain type. We have to improve the trafficability of the rover, the wheel. So there we concentrated morely to optimize the wheel dimensions. Like, you take wheel weight, wheel diameter, wheel width. So all these things we focused on particularly that. Okay, when you increase the weight, how does it affect? It reduces these parameters, or it is increasing the parameters. When you add the lugs, whether it is increasing the performance or decreasing performance, how it is giving. So that kind of studies only we carried out. This actually the more circle theory and all we didn't consider for the study. Anyone else want to add up something? I thank everyone whoever is posting in the chat box. Yes. I thank all the professors and all the faculties for taking time to attend this 1 week short-term training program. I'm really happy for all of you. And we will definitely, again, we will meet for the phase 3. Thank you. So there is an assessment for all of us. So assessment will have a 25 questions or something simple questions. You can take some time to finish it. 10 to 15 minutes. That assessment link also I'll post into few minutes. Yeah, one or two can unmute yourself and talk so that we can listen. No, soil varies because here you see we have a soil types we take. We have a sandy type, clayey type, loam type, talus type, and silty loam clay type. So different types of soils we have. Actually, on Mars or a moon, that is different completely. Okay, we cannot define as it is a silty or it is a clay or it is a talus and all. But most importantly, whatever we characterized, like a TRI1, that actually we got a cohesion of 0.36 and internal friction as 43, which actually represent a loam type and what to say silty loam type, which is will be nearly closer to that. Okay, yeah. So that is how you can relate that internal friction angle as well as this one. Okay, thank you. So I hope the assessment link I will provide, sir. Maybe now in few minutes, in 2 minutes, I will provide assessment link. Yes, sir. I'll provide. Anyone want to add something? You can just unmute and talk so that I'll post the. Maybe you can use the assessment link between 1 to 2:30, something like that. We will open the link. Then meanwhile you can attend that link anytime. Hello.
Hello.
Sir, hello. Yes, sir.
This is Sundar Kumar, sir.
Sir, good afternoon, sir.
Very good afternoon, sir. This is Dr. P. Sundar Kumar from
Yes,
Bapatla Engineering College.
Good afternoon, sir. Yes,
Good afternoon, sir. As a professor, Department of Civil Engineering, sir. First of all, thank you given the opportunity for sharing some words regarding this FDP. I want to thank you very much for your excellent management. What has turned to successful, highly stimulated FDP, faculty development program. Like,
yes,
I am sure that everyone must have told this. Such a conference involvement, enormous amount of time and energy. You must have been working so hard, literally for everything to fall into the place it has. You deserve now as well as earnest rest. Thank you, sir. And as well as especially attend the program first all days, almost all, but some some topics I'm not able to attend because of class are started in my college. But Nagesh sir and from IIT Bombay, Igno sir, I attend the program on both the topics. Really enjoy because I am the water resource person. Thank you, sir. You bring the very talented person who are conducting the such a level, top level, and successfully complete this program. Thank you once again for giving this opportunity. Thank you, sir.
Thank you, sir. Thank you, Professor Sundaran, sir. Very much thankful for your words. And yes, sir, we understand that because we all have online classes. Yes, it is difficult to present all. Yes, thank you, even though you have attended, sir. It's very nice to meet you, sir. Nice to meet you once. Maybe when we will meet personally later, once if it is possible.
Okay.
Thank you, sir. Thank you.
Thank you, master. Thank you. Well done.
Good afternoon, sir. Hello.
Sir, good afternoon, sir. Yes, sir.
Good afternoon, sir. This is Dr. Sairam Kumar from RVR and JC College, Guntur, sir.
Okay.
Sir, a good session is made by your organization and you, sir. Very nicely organized, sir. And the topics also covered are very informative, sir. Those are very innovative and informative. And somehow I have not listened to this topic in the previous workshops also, sir. Some topics are very innovative and very impressive to learn in this free time, sir. I'm very thankful to your organization for making me inviting to this workshop, sir. Thank you very much, sir.
Thank you so much, sir. Thank you so much for your attending this workshop, sir. We are very really happy. and for these words. Yes, sir.
We are further also we are going to view for your AICTE workshops or whatever maybe the webinars or sessions, sir. We will try to
Definitely. participate
and make it successful, sir. Thank you very much, sir.
Excellent, excellent support, sir. Excellent support. Thank you, sir. Thank you so much.
Thank you very much, sir.
Hello.
Yeah, hello, sir.
I am Dr. Selvan from Kumaral College of Technology, Coimbatore.
Yeah, sir. KCT. Yeah, very nice
yes,
to meet you, sir. Once again. Good afternoon.
Good afternoon, sir. The FDP webinars are excellent, sir. The resource person has given an excellent session to know the various technical details of recent trends. We are very much thankful to all the resource person, and thanks for the organizers, and congrats to the institution and the organizer in a very well organized manner. Thank you very much, sir.
Yeah, thank you, sir. Thank you so much, sir. I am seeing you every time, sir. Very
Yeah.
supportive from your side. I'm very thankful for your support, sir.
Okay, sir.
We look
Thank you,
forward
sir.
to- Thank you, sir. Yeah.
Thank you.
The assessment is link provided in the chat box, so you can use the assessment link till 2:30. Till 2:30 it will be open, so you can give whenever you are free. And there is one question from YouTube. I want to address that question. Yeah, the gravity effect, will it have a serious effect? Yes, of course. The gravity, moon's gravity is 1/6 of Earth gravity. That actually we know generally. So what we have to do is, whatever the models that we are developing, or we are involving the G factor, the gravity factor. Whatever the gravity of Earth is 9.81 meters per second square, or whatever it is, 10 or around 10 you can take, where the moon's gravity is one sixth of it. That you can consider and do it. Sometimes in ISRO and NASA, they are having particular system called that gravity. Also, they will consider by doing the experimental part. So definitely that affects the results. You need to consider that gravity parameter. Otherwise, the entire results are going to be changed, because we need to differentiate the terrestrial surface results as well as extraterrestrial surface results. Yeah. You need to account that gravity effect.
Thank you, sir.
Yes, sir. Please continue, sir.
I am
Yes, sir.
Rajeshwar Rao.
Sir, good afternoon.
I am executive engineer in Mission Bhagirath.
Oh, excellent, sir. Excellent. Welcome, sir. Yeah.
Almost very few classes based on time availability. I also attended. Very good. All the sessions are very good and informative, and all the innovative also there. I am very congratulations to your institution as well as all the resource persons who are presented very good, excellent papers. Hats off, and that should be implemented. Whatever the innovations are there, which are suitable to the Indian environments, we have to implement it. Please try in that aspect. Only implementations only for beneficiation of the our nation.
So,
thank you very much.
Thank you very much, sir. Such a wonderful words, sir. We will take your suggestions into account. We will also try to bring awareness to various people. Thank you so much. Thank you so much, sir.
Thank you.
I see a lot of comments in the chat box. I personally thank each and every participants. Definitely, I must be very thankful to all the participant presence. Yeah, if someone is asking about the friction, yes, an external body. Yeah, that when you call it as, we have something called a resistance. Okay, so that is a resistance against friction that normally we have a gravitational and compaction and bulldozing as well as motion. So where when you go with the slopey terrain, this gravitational resistance comes into picture in order to counteract that friction, and as well as when you compact, or when you get that less compaction, you must have through proper analysis, you must have a less bulldozing resistance. And obviously, when you have this less compaction resistance, less bulldozing resistance, and less rolling resistance, and more gravitational resistance, it is obviously gives a good and a better mobility for a rover. Anyone else? Sir, actually feedback is shared, as well as the assessment link is also shared in the chat box. So the assessment link will be opened till 2:30. You can have your assessment anytime whenever you are comfortable. It hardly takes 10 minutes. Yeah, friction about the external body of a robot. Yeah, it is not that serious thing that you need to consider, because you see we hardly give some kind of suspensions or some kind of very less body. Largely we were considered mostly on this amount of types of wheels you are giving. Suppose you take a 6-wheeled, 8-wheeled, that is equally shared, or a 4-wheel or a 2-wheel, like that. Anybody wants? I thank the coordinator of this workshop, our Professor Venkata Raju sir, and also I thank my faculty coordinators, Manasa madam and Bharati madam, for supporting me throughout this workshop, and I thank my college for giving opportunity to what to say, conduct this such program, and also I thank the AICTE for sponsoring for this workshop. And yes, I want to conclude this. Same problem. Yeah, feedback link. If you are not able to get, you are requested to send us a email at any time. We are able to respond to you. Yeah. Anybody want to share one or two more? Then we will stop this. We'll end the session.
Thank you.
Madam Manasa, madam, you can close the session,
Sir.
madam. Yeah,
Okay,
please.
sir. Thank you, sir. Thank you, sir. I thank Dr. Girish for giving an excellent session today, and I thank all the resource persons who had already given the sessions, their valuable sessions and their valuable advices, as well as the valuable subject they had given. I also thank all the participants for bearing with us, and also participating in every webinar and making this a grand success. Also, we thank all the department faculty and all the organizing team. We thank them a lot. In particular, I thank Dr. Pala Girish Kumar. I particularly thank Pala Girish Kumar for conducting this type of webinar, and also I thank all my co-faculty members and all the participants and the AICT sponsors and everyone for making this particular webinar a grand success. Thank you, one and all. The assessment link is provided in the chat box. You can use that between 2 to 3 o'clock, and you can give your valuable feedback and assessment there. Thank you. Thank you, one and all.
Thank you so much, madam. Yeah. So, can we close now? Once again, you just share the certificates. We will try to send you by 31st of this month. Okay.
Yeah, we are about to close our session.
Yeah.
Sir, shall I close the session?
One more minute, ma'am. We will share one more time that feedback as well as assessment link so that
Okay, sir.
maybe if
Okay,
anybody is missing, they can have that. Okay.
Okay, sir. I'll share
Yeah.
it.
Yeah. Please share that feedback link and mention that is feedback. Share
Okay, sir.
assessment link and mention that is assessment link. Okay.
Okay,
Yeah.
sir.
Do that. Do that. Yes. Yes. Dear participants, the feedback link is given as well as the assessment link also will be given again. Just try to see, don't get confused. First one is feedback link, second one is assessment link. Both are different, madam. Manasa madam, hello.
Oh, sir. Sir.
Both are
Sir.
different, no? Both links are different, no? Because I
Different,
see
different.
similar names. That is different, no? Just check it.
Yes, sir. Second one is assessment link, sir.
But I see same. It is of same type names given in the same, but it is different, no?
Yes, sir. Oh, sorry, sir. Wait.
Please do
I'll
that,
just
madam. They will
repost
get
it again.
reposted. So
Thank you, sir.
dear participants, that is the feedback link. Okay, now we will send the assessment link. Very sorry for this inconvenience.
The links are posted again. You can find feedback link and the assessment link. The both are different links. You can give your feedback now, and assessment link will be opened after 1 o'clock.
Uh, Excuse me, sir. Assessment link is also working, and I am trying to answer it also.
Yeah, please do that, sir. It will be remaining open till 3 o'clock, sir.
Okay.
Okay.
Thank you.
We will close that at 3 o'clock.
Okay, thank you, sir.
The assessment link also we received.
Yes,
this
sir.
week.
Please go ahead, sir. Yeah, please do that. Sir.
Can I fill that one or otherwise wait
Yeah,
for one?
sure. You can fill, sir. We will open that till 3 o'clock. So you can do it now. Sir. No
Okay,
issues.
thank you.
Thank you, sir. I hope you have all received that feedback as well as assessment link, and hopefully you will be doing that. Okay. So if in case if you get any problem, we are at your end to support through mail. So you can write us on the mail given in the chat box. I think you have my mail already, but still I will write more time. I request the participants to try to we will send you a certificate by within a week, or it will come before 30th of August, because we are parallelly doing conference works also. That is why it will be a bit delayed. But definitely, if you are not reaching by 30th of August, you can write us a mail, then we will address it. Thank you so much. So this is the mail ID. You can approach me at any time about anything. I'm happy to reply to your queries. And I take this opportunity to end the session. So we'll hopefully meet in some other time, in some other event. Thank you, and I wish you each and every person a very, there is, no, there is no minimum mark or maximum mark. Just we gave a simple assessment just for a record, because we need to submit to AICTE. So for that purpose, we are taking this assessment thing. Okay, thank you. Happy Vinayak Chaturthi to you all. Yes, thank you so much. So with this, I am just closing this. Maybe if you are not having any problem, we will just address through mail. Thank you so much. It was nice meeting you all throughout this week. Hopefully, we will meet again in certain platform. Thank you one and all. And signing off for today and for this event. Thank you.